When I have an equilibrium expression like we looked at here, we have a ratio of products to reactants. And that ratio corresponds to a numeric value. That's why it's a constant. There's a few down here where we have, in both of these cases, big numbers. So we could be given the K for a reaction and asked to solve for concentrations or asked to describe a graph, draw a picture, or understand relative amounts. But sometimes we have information about pieces of a reaction, but not the whole reaction. So this is a great example down here that you'll see on the practice sheet, but where we want to know about a certain equilibrium that we don't know its value. But we do know about equilibriums related to it. We do know about other equilibriums involving those same chemicals. Very similar to the way we can approach Hess's law in terms of energy and enthalpy. If we have equilibrium expressions involving the same chemicals as our desired equilibrium, we can manipulate or think about the different way to write those expressions and understand or put them, combine them to make an overall K. So probably the most common is actually the middle one here. If I have an equilibrium with reactants on one side and products on the other, if I were to think about that reaction in its reverse, changing what we define as reactants and products, we would still have the same reaction, but now our numerator becomes our denominator and our denominator our numerator. So the reciprocal of our original K is what our new K is equal to. So that's something we can use to think about, well, if the reaction's going this way, how favorable is it? Therefore, if it's going the other way, does it change? And it does change in terms of its favorability, going back to energy and disorder. We can also, when trying to put reactions together, maybe need more or less of a certain reactant or product. In that case, if I change all of my coefficients, then that changes what the exponents are within my K expression. And when I change the exponents within my K, that new set of coefficients, whether they're doubled or tripled, would then become an exponent on my K. If all of my coefficients were a 2, then all of my exponents would become a 2, and therefore K would be squared in terms of its value. Once we had all of our reactions with the correct values, with the correct things on the correct side, so maybe we reversed reactants and products, or maybe we had to change our coefficients, we then want to combine all of those so that they cancel out to make the reaction we're looking for. When we combine them, all of those new K values or those different K values are multiplied. So the sample problem has some really good examples of this, but this is something you could see multiple choice or free response, sometimes wanting exact values, or sometimes just estimating. Is the new K going to be very big or very small based upon the magnitudes of the original K? So great practice here to get an idea, and even as you're doing it, maybe to estimate whether the K will be big or small.